So the last talk of the session will be given by Matthias Kern. So Matthias graduated last September with a degree in embedded systems design from FH Hagenberg. During his studies, he worked as a student employee in the component verification laboratory at Infineon Linz, where he developed various FPGA-based tools. Since November 2024, he's been working as an FPGA engineer at P2L2. So Matthias.
Yeah, hi everybody from my side. Is it mic working? Closer? Is it working? Yeah. Okay, nice. So again, thank you, Matthias, for the nice introduction. Welcome everybody to my talk about HDL co-simulation with AMD Alveo using open source tools. I did this project as my master thesis, so yeah, let's get started. Okay. Yeah, we can skip this slide, as we saw it an hour ago. What am I going to be talking about today? I'll start with what I consider as a typical design plus test bench setup. I'll then continue by explaining what the co-simulation concept is about. I'll introduce the open source tools I used for realizing this concept, and then I'll show some benchmarks I did. And I'll conclude by showing some other applications and limitations of my system, as well as sharing the current state of the project. So what is a typical FPGA application in my point of view? There's some input data sink, some input data source, some processing happening, and then there's also some output sync. Maybe there's some configuration interface, but typically what I saw is that the activity on this interface is quite low. And also input and output are mostly or often use finished IP components from your FPGA vendor. And so the main implementation effort can be put or should be put into the processing stage. The typical test bench, or what I consider as a typical test bench, you have a test bench for each separate part of the design, and then especially for signal processing applications, you should put every part of the design together into one test bench and verify it against your golden model that you wrote at the beginning of the design in some high-level language, maybe Python, maybe MATLAB, and yeah, to verify that the HDL code you wrote matches the bit accurate model. And every FPGA design will result in something like shown in the bottom. There are some flip-flop stages and combinational logic in between. And so what's happening in the simulation is that the combinational logic needs to be re-evaluated every single clock cycle at least once if there are some changes at the input of the combinational logic. And so let's just have a quick look at the simulation cycle. It's the C abstract machine for VHDL, and it's specified in the VHDL language reference manual. I'm sure there's something similar for Verilog, but I'm just familiar with the VHDL system simulation cycle. And the simulation cycle defines what the simulator should do, when, and how. And if you remove all the complicated edge cases and you boil it down, it just condenses into 3 simple steps that suffice for most RTL code. And that's just executing all active processes. Then you determine the next time a signal driver becomes active, and you update you then proceed to this next time step and update the driving values of the signals with the next value. And you do this every time, or a lot of time, until you stop the simulation. And especially if you have multiple processes in series between register stages, then you need to iterate these 3 steps multiple times per clock cycle. So now let's talk about the co-simulation concept. My idea is to just offload the device on the test and put it into an FPGA and connect the input ports of the design in the simulator with the input ports in the FPGA, and do the same for the output ports. So the offloaded design, it lives fully in the FPGA, and the simulator has an empty architecture, so there is no work to be done for the device on the test. What we then do for every clock cycle is to read the values at the inputs, move them to the FPGA, and perform a single clock cycle in the FPGA. Then we capture the outputs in the FPGA and move them back to the simulator. What results is that every design can now be simulated in 1 clock cycle on the FPGA, which can be, depending on the size of the design, quite a big saving. We now move from a design size constraint to a port size constraint. So the simulation time is now depending only or mainly on the transfer of the port values to the FPGA and back to the simulator. And the actual simulation of the design is negligible. And with just extracting the architecture from the simulator, you can reuse existing test benches and use the system as a drop-in replacement. What this does, if you look at the higher view from it, it's just simulating the design in a cycle-based manner instead of the previous event-driven manner. So we need now 2 things to realize this design, and the first one is to a simulation extension interface. In the previous presentation, we already heard about them. VHDL, Verilog, and System Verilog all define interfaces for extending simulator at runtime so you can load a shared library into the simulator and perform a user interface to explore the structure or hierarchy of the currently simulated design. You can attach callbacks on certain events, and you can read and update the signal values of the design. For that, there is CocoDB. I'm sure most of you already know this tool. So CocoDB is a co-simulation framework for writing test benches in Python, and it launches the Python interpreter after the simulator started. So CocoDB works by also loading a shared library into the simulator, and after the simulation has started up, CocoDB then launches the Python interpreter and executes the test bench code alongside the simulator simulating the design. CocoDB supports a lot of simulators, and this does this by introducing an abstraction layer on top of the simulation interfaces, which it calls GPI. And the GPI then provides a common interface for VHPI for VHDL, VPI for Verilog and System Verilog, and GHDL as we heard previously, and the FLI interface, which is used by ModelSim or QuestaSim. By default, the GPI is CocoDB specific, so without modification, if you just look at the code in the repository, then it always starts a Python interpreter on the startup. And in my master thesis, I extracted the GPI from CocoDB and made it usable for standalone applications. So now we have an interface to the simulator. We just need now an interface between the CPU and the design in the FPGA, and for that I use the Coyote project, which is a framework for operating system-like abstractions in an FPGA, and it is developed by the Institute for Computing Platforms or Systems Group at ETH Zurich. And what it does is it partitions the FPGA into multiple blocks that you can each put a design in, and it provides interfaces and also the configuration interface, a build system, and also handles the communication and the Linux driver for sending data via the PCIe interface. Now we have everything together to look at the actual implementation. We have the GPI for communicating with the simulator, and we have Coyote for communicating between the CPU and the FPGA accelerator. For hardware, I had available an Alveo U55C from AMD, which I used as FPGA accelerator, and the CPU was a Zen 2 EPIC processor. The actual implementation, so what the co-simulation library does is it sets up so it is loaded again dynamically into the simulator. It sets up Coyote. It gets handles to all the port signals of the offloaded design, and it attaches a rising edge callback to the clock signal. And then this callback performs the data exchange with the FPGA accelerator. Inside the FPGA, we just need to accept the data from an input stream, apply it to the device under test, and only perform clock cycles if we receive input signals, so that the design under test stays synchronized to the state in the simulator. We then, after the clock cycle, we then capture the outputs and send them back to the simulation interface, where it gets written to the output port signals of the device in the simulator. So for benchmarking, I had available an FMCW frequency modulated continuous wave signal generator from a digital radar system. It has a configuration interface on the input where you can set the ramp parameters and also apply some amplitude and phase corrections on the actual outputs. And so it has two outputs that go to the RFDC and an RF-SOC FPGA, and two monitor outputs that are going to the mixer. And I looked at two test cases. So the first test case was just for visual inspection of the resulting waveforms. And I also had a high overhead test where I generated expected results using a bit accurate model in Python and compared them to the outputs of the design under test in the test bench. Everything is done with UVM verification components. And so for the results, for the low overhead test, we see almost 3 times speed up for NVC, and also almost a doubling in simulation, halving in simulation time for QuestaSim. But with the high overhead test, the benefits get smaller. And if we look into the results in a bit more detail, I measured the times between two rising edges and calculated the statistical properties. And for the low overhead test, we can see that 10 microseconds are spent, so in the 10 microseconds are spent in the cumulatively on average in the co-simulation library, and another 110 microseconds are spent in the simulator. So even though we offloaded or sped up the design by quite a big margin, we still spend a lot of time in the simulator. And for high overhead results, for the high overhead test bench, we spent a lot more time in the simulator. So even though we sped up the design considerably, the simulation did not speed up as much because the simulation overhead, the test bench overhead was too big. But still, we see that the time spent in the co-simulation library is small. So for applications, obviously there's speeding up simulations for large designs. The larger the design or the bigger the ratio of design to test bench is, the better the simulation speed up will be. Because you are synthesizing the design and putting it into the simulator, you now verify the synthesized design. So you can check the results of the synthesis tool and not just trust it. And because you can synthesize encrypted IPs, you now can also simulate encrypted IPs and integrate physical hardware into the simulation. Some limitations, obviously, for the design to be synthesized, it first needs to be synthesizable. And with this co-simulation system, you can only simulate synthesizable designs. In the hardware, there are no meta values, so only zeros and ones are supported. For now, there's only a single clock domain supported, and as you cannot just open the hierarchy in the simulator, because there is no more hierarchy, you cannot just access internal signals in the design. So there's limited debuggability. And because we transformed the design under test into a cycle-based evaluation, there may not be any combinational dependencies from the output ports to the input ports. And this is because we only update the values once per clock cycle, and combinational outputs would be updated before the next rising edge. So there is a discrepancy between the simulation and the co-simulation. Current state, it's more just a proof of concept that this is actually working, and as we saw, it did. What's next is the automatic generation of the co-simulation library and the simulation adapter from the DITs, because we just need the path to the device under test in the hierarchy and all the port names, so we can get the handles, and then it just needs to automatically handle the transmission of the port values to the FPGA accelerator and back. What's also needed is more testing, more benchmarking, especially with larger designs. And the Coyote project supports a lot more features that can be beneficial to this project. So there are some maybe some extensions that can be performed. With that, I conclude my presentation. Thank you very much for your attention.
Thank you, Matthias, for sharing these very interesting results. Any question?
Yeah, thanks for the very interesting talk. I have a question on, do I have to adapt my device under test, like the port structure in any way, in order to make it compatible with the Alveo kernel standards? Because I don't know what like Coyote is using in the background when when building or like when putting together the design for Alveo, but I know that for Alveo kernels, you can only have like a certain configuration of AXI interfaces at the top level of your module. And what does that look like for my device under test with your framework? Can I just use individual bit lines and it gets converted to something that Alveo can handle, or do I need to adhere to their AXI port structure?
No, you don't, because you just offload the simulation design under test. So if you have a simulation, then there are just some studio logic vectors or studio logics or any other zeros and one values. And you transform this into some sort of representation in a C structure, and this then gets transmitted via PCIe to the FPGA accelerator in binary. So anything that is representable in binary can be transmitted, and then can be port type. So there are no real limitations here.
So thanks a lot for your presentation. I'm trying to understand exactly the application of this particular project. So it's very interesting how you implemented this. But so let's say I have a very large design that I want to simulate. But to put it on the Alveo card, I imagine that I still needed to synthesize it, no? So this is still some time that takes, and maybe, I don't know, my design is also targeting a different FPGA at the end, so I'm not sure if I can just copy and paste my design and put it there. So what would be the advantage of using this particular method with respect to a standard simulation framework where I target the particular part, let's say?
One concept I thought of was black box testing. So if two teams develop, or a separate team develops the test bench from the actual component, then the test bench can be developed synchronously or at the same time, and then maybe the test bench takes ages to simulate because it is constrained random and it runs for a week, and then maybe the synthesis process takes shorter than the speed up gained from offloading the design to the FPGA. That's one application I thought of. And then obviously verification of the synthesis. So that the design still does the same thing after synthesis, because that's you don't, or in my I never performed post-synthesis simulation, and this is running on real hardware, so it's as close as as close to the actual design as it can get.
Hi, also thanks for the great talk. Maybe on that, did you consider an approach where you only took a certain part of your design and co-simulated that? So you have like a outer simulation of a part of your design that you can rapidly exchange and simulate, and maybe some IP core that you cannot simulate that you would then offload to your co-simulation approach?
Obviously, that's again possible, as you can not just offload the complete device under test, but just a separate part of it that's contained into a single entity, and then you simulate part of the design still in the simulator and offload the rest to the FPGA. Yes, that's also possible.
So I'm wondering how much setup does it take to, let's say, bring my, let's say, some core that I'm testing right now. So I imagine that I have to prepare all of the I/O handling and so on for my design, right?
Yeah, for now you have to write the co-simulation library, so the part that traverses the design, finds the ports, and then structures the port values into something that can be sent to the Alveo card and received back. But this should be automatable. So the end goal is just to run a script that creates everything, and then you run the synthesis and run the simulation. So no manual labor is involved then.
Okay.
Yep.
Thank you for the interesting presentation. Just one simple question. Like, I did not understand. The clock is generated by the simulator, like co-simulator.
The clock, so you don't want a generated clock in the FPGA. So there's just a clock gate in between to only run a single clock cycle when there is new data, to keep the device synchronized with how it would have been in the simulation.
So the clock is still coming from the oscillator or whatever it is on the board?
I didn't transfer the clock value. I just transferred data, and then the FPGA accelerator knew that there was new data, and it would perform a single clock cycle then, yes.
Thank you.
No more questions? Oh, sorry.
So it's very interesting, but I have a question. So I would assume that because you're using a physical thing to simulate, how do you simulate, for example, when this PCI Express card is up and running? I mean, it needs to be up and running for you to start the simulation, but maybe you will be interested in how the things are starting, right? I mean, maybe there's a secure IP and you want to see during the initialization of the FPGA, like you want to look at the behavior. It looks like this solution is mostly like when everything is up and running and then you kind of gate the clock and you look at the transition. So, like, is there a limitation on that? So if I want to look at, like, I'm trying to point out that this PCI Express card needs to be basically fully functional with PCI Express for you to then start simulating these things, right?
Yeah, that's true. But the design is not directly put into the FPGA accelerator, but there's logic around it. And you then have the design being reset like it would have been in the simulation. So you start from the beginning because you transmit the reset also to the offloaded part. And when the reset is 0, then all registers get reset because the design is a part of so the device under test is part of the design in the FPGA. But there is logic around it. So you are, for this concept, the FPGA has to be configured and running, but the design is behaving the same as it would have been in the simulator. So you already see it from the beginning.
Okay.
Last one.
So there is a question from Discord. So it's similar to the question that has been asked previously on the clock frequency. But I think the main question is about if you apply some special constraint, you run the design under test with a lower clock frequency to meet timing on the Alveo, or you keep the same frequency that the design is supposed to run?
You can. I run the design at 200 megahertz, and it does not matter because it just needs to be synthesizable. And if it meets the timing in the synthesis, then this does not correlate in any way with the actual frequency that the design is running in the real hardware in the end. It's just like simulation. You can set the simulation frequency to a gigahertz, even if the design would never run at a gigahertz. So these frequencies are decoupled.
This maybe my curiosity. Do you handle also multiple clocks?
I'm sorry?
Do you handle multiple clock frequencies?
For now, I did not implement multiple clock frequencies, as I said in the presentation, but in theory, it should be possible with a similar approach to just add more clock edges.
Okay, so let's thank Matthias again.